Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. What alien civilizations might actually look like? When most people imagine alien civilizations, they picture humanoid beings with large heads, slender bodies, and advanced technology that allows them to cross the vast distances between stars. Science fiction has given us countless variations: green-skinned Martians, insectoid hive minds, crystalline energy beings, peaceful explorers, and hostile invaders alike. But what would alien civilizations actually look like if we base our expectations on biology, physics, chemistry, and evolutionary principles rather than imagination alone? The answer reveals possibilities both familiar and utterly strange, shaped by the same fundamental laws that govern life on Earth, but expressed through the infinite variations that different worlds and evolutionary histories would create. The foundation of any alien civilization begins with evolution. On Earth, every organism exists because its ancestors survived and reproduced more successfully than competitors. Natural selection shaped everything from bacterial flagella to human brains, optimizing organisms for their specific environments and challenges. The same process would operate on any world where life exists. Alien organisms would be shaped by their planet's gravity, atmosphere, temperature, available nutrients, predators, and countless other factors operating over millions or billions of years. Evolution is relentless, creative, and opportunistic, finding solutions to survival challenges through whatever mechanisms work. Gravity would profoundly influence alien body structures. On a high-gravity planet, perhaps 1.5 times Earth's gravity, organisms would need stronger skeletal structures to support their weight. Animals might evolve shorter, stockier bodies with thicker bones and more powerful muscles. Tall, slender forms would be disadvantageous because they would require too much structural support and energy to maintain. Intelligent beings on such a world might stand only 3 or 4 feet tall despite being as massive as humans, with powerful legs and low centers of gravity to move efficiently under the stronger gravitational pull. On a low-gravity planet, the opposite constraints would apply. With less gravitational force to overcome, organisms could grow taller and more delicate. Bones could be lighter and more slender. Flying might be easier, allowing evolution to produce larger flying organisms than Earth's giant pterosaurs. Intelligent beings might stand 8 or 10 feet tall with elongated limbs, moving with a grace that would seem almost balletic to Earth-based observers. Their skeletal structure might resemble bird bones, hollow and reinforced with internal struts rather than solid like mammalian bones. The atmospheric composition would shape how aliens breathe and what biochemistry they use. On Earth, most complex life uses oxygen for metabolism because burning fuel with oxygen releases large amounts of energy efficiently. But oxygen was not always abundant. Early Earth had an atmosphere dominated by nitrogen, carbon dioxide, methane, and other gases. The oxygen we breathe today came from photosynthetic bacteria that gradually transformed the atmosphere over billions of years in what's called the Great Oxidation Event. An alien planet might never undergo such a transformation, leaving its atmosphere oxygen poor. Life there might use different metabolic pathways, perhaps based on sulfur compounds, hydrogen, or methane. The type of star a planet orbits would influence alien vision and perhaps their entire sensory experience of reality. Our sun emits most strongly in visible light wavelengths, the colours we can see, and Earth's organisms evolved eyes sensitive to these wavelengths, because that's where the most light was available. But a planet orbiting a red dwarf star would receive most of its light in infrared wavelengths. Organisms evolving there might develop eyes sensitive to infrared rather than visible light. To them, what we call visible light might be invisible ultraviolet, and their daylight would be our infrared. An alien from such a world would perceive colours and see objects in ways completely foreign to human experience. Conversely, a planet orbiting a hotter, bluer star would receive more ultraviolet light. Evolution might produce eyes sensitive to ultraviolet wavelengths, allowing these aliens to see patterns and colours invisible to humans. Many Earth organisms, including bees and some birds, can already see into the ultraviolet range, perceiving patterns on flowers and plumage that humans cannot detect without special cameras. An alien species with full ultraviolet vision would experience a visual world enriched with information and beauty we cannot access. Communication methods would evolve based on environmental constraints and available sensory channels. On Earth, humans primarily communicate through sound, speaking and hearing, supplemented by visual cues like facial expressions and gestures. But sound travels poorly, in thin atmospheres, and not at all in vacuum. An alien species on a world with a thin atmosphere might rely more heavily on visual communication, colour changes, bioluminescent patterns, or elaborate gestural languages. Octopuses on Earth already use colour-changing skin cells, called chromatophores, to communicate, creating flowing patterns across their bodies. An intelligent species with similar abilities might communicate through rapidly shifting colour displays, conveying complex ideas through patterns that flow across their skin in what would appear to us as living art. Some aliens might communicate through vibrations transmitted through the ground or through their planet's oceans. Whales and elephants on Earth use low-frequency sounds that travel great distances. Elephant calls can travel several miles through the ground. An intelligent species might evolve specialized organs for creating and detecting vibrations, communicating through seismic signals that travel through rock or sediment. Their language would be invisible and inaudible to humans without special equipment to detect the vibrations. Chemical communication, already used extensively by Earth's insects through pheromones, might become the primary communication method for some species. Aliens might communicate through releasing complex mixtures of chemicals that other members of their species detect through sensitive chemoreceptors. Their language would consist of scents and tastes, with grammar and syntax encoded in the ratios and combinations of different molecules. To humans, their most profound poetry and scientific papers would be nothing more than smells. Body structure would reflect evolutionary history and environmental pressures. The bilateral symmetry seen in most Earth animals, a left side mirroring a right side, emerged early in evolution and became locked in. But aliens might evolve radial symmetry, like starfish, with body parts arranged around a central axis. An intelligent being with radial symmetry might have arms, eyes, and sensory organs distributed evenly around their body, giving them a 360-degree field of awareness with no natural front or back. Their psychology and culture might be profoundly affected by experiencing the world without a preferred direction of travel or attention. The number of limbs is not fixed by any physical law. Earth's vertebrates settled on 4 limbs relatively early in evolutionary history, but arthropods, insects, spiders, crustaceans have 6, 8, or even dozens of legs. An alien species might evolve with 3 limbs arranged in a triangle, giving them stable tripod support at all times. They might have 6 limbs, 4 for walking and 2 manipulator arms. Or they might have dozens of tentacles like an octopus, each capable of independent complex movement and manipulation. Their tool use and technology would develop along entirely different lines than human technology, shaped by their different manipulative abilities. Intelligence itself might manifest in forms unlike human intelligence. Human intelligence is highly centralized. Most of our cognitive processing occurs in our brain, a single organ in our head. But octopuses, among Earth's most intelligent invertebrates, have a distributed nervous system with neurons throughout their arms that can make independent decisions. An alien species might have multiple brain centers distributed throughout their body, or they might have a collective intelligence where individual organisms are relatively simple, but groups display emergent intelligence through their interactions, similar to how ant colonies solve complex problems that individual ants cannot. Social structure would influence civilization development. Humans are intensely social primates who naturally form groups, cooperate, compete, and create complex hierarchies. An intelligent species that evolved from solitary predators might have very different social instincts, perhaps coming together only to mate and raise young, then separating again. Their civilization would be built by individuals who value isolation and independence over community and cooperation. Or aliens might be eusocial, like bees or ants, with specialized castes, workers, soldiers, reproducers, genetically programmed for different roles. Their civilization might function as a superorganism where individual identity barely exists. Lifespan would profoundly affect culture and technology development. If an alien species naturally lives for thousands of years, they might approach problems with a patience humans cannot fathom, willing to spend centuries on single projects. Their sense of urgency and change would operate on timescales that would frustrate any human trying to interact with them. Conversely, a species with lifespans of only a few years might compress their entire cultural and technological development into periods that humans would find incomprehensibly rapid. Environmental factors would shape not just biology, but psychology and culture. A species that evolved in oceans might think about space and boundaries very differently than land-dwelling humans. Without solid ground beneath them, without permanent structures that last for generations, their concepts of property, territory, and permanence might be fluid in ways humans struggle to understand. A species that evolved in dense forests with limited sightlines might have very different concepts of distance and perspective than humans who evolved in open savannas, where seeing for miles was possible and valuable. Technology would develop based on available resources and environmental challenges. A civilization on a water world with no dry land would never discover fire, fundamentally altering their technological development pathway. Without fire, they couldn't easily work metals, make pottery, or develop steam power. Their technology might focus on biological engineering, breeding organisms to serve specific functions, or on working with materials that don't require heat processing. They might develop advanced understanding of hydrodynamics, pressure, and acoustic phenomena, while lacking technologies that humans developed early. A civilization on a planet with extreme temperature swings might prioritize insulation and environmental control. A species on a tidally locked planet with one side in permanent daylight and the other in eternal darkness might build their civilization in the twilight zone between extremes. Or they might develop two separate cultures adapted to the radically different environments. Their technology would need to handle these extremes, perhaps leading to advanced materials science long before other fields developed. Reproduction methods would influence family structures and social organization. If aliens reproduce through spawning like fish, releasing eggs and sperm into water where fertilization occurs externally, they might have no concept of nuclear family or parental bonds. Eggs might be raised communally or even left to develop independently. If reproduction requires 3 or more sexes simultaneously, their social structures and mating rituals would be incomprehensibly complex to humans. If they reproduce through budding or fission, creating genetic copies of themselves, their concepts of individuality and identity might be fundamentally different from species that reproduce sexually and value genetic diversity. Sensory experiences beyond human comprehension might exist. Some Earth organisms detect magnetic fields, electric fields, pressure changes, or polarized light, senses humans lack entirely. An alien species might perceive reality through senses we don't possess and cannot easily imagine. They might see the world through echolocation like bats, building a sonic map of their environment. They might sense electrical fields like sharks detecting the bioelectric signatures of other organisms. They might perceive time differently, with reaction times much faster or slower than humans, making their subjective experience of duration incompatible with ours. The Fermi paradox asks why, if alien civilizations are likely to exist, we haven't detected them yet. One possible answer is that we're looking for the wrong things. We search for radio signals because that's how we communicate, and we look for visible structures, like cities, because that's how we build. But an alien civilization might never develop radio technology, using entirely different communication methods. They might build in ways that leave no visible trace from space. They might exist on entirely different timescales, civilizations that rise and fall in centuries, while humans are still learning to farm, or civilizations that operate so slowly that their entire recorded history spans less time than a human lifetime. If contact ever occurs between human and alien civilizations, the challenges would be immense. Even if both species are trying to communicate, fundamental differences in sensory experience, cognition, timescales, and conceptual frameworks might make mutual understanding nearly impossible. Imagine trying to explain color to someone born blind, or music to someone born deaf, or love to a species that doesn't experience emotions. Now multiply those challenges by every aspect of existence: time, space, causation, identity, purpose. Communication might require generations of effort and specialized translation technologies we haven't yet imagined. What alien civilizations might actually look like encompasses possibilities ranging from vaguely familiar, carbon-based organisms breathing oxygen on Earth-like worlds, shaped by convergent evolution into forms somewhat similar to Earth's creatures, to utterly incomprehensible beings whose very existence challenges our definitions of life, intelligence, and civilization. They might be silicon-based entities living in molten rock at temperatures that would vaporize Earth's organisms. They might be electromagnetic patterns in planetary magnetic fields, or chemical reaction networks in liquid methane seas, or quantum coherence patterns in neutron star crusts. The universe is vast and ancient, and if intelligence has emerged elsewhere, it has had billions of years and countless different environments in which to develop into forms limited only by physics, chemistry, and the creative power of evolution operating across deep time on worlds we've never seen. What intelligent alien technology might reveal? The search for extraterrestrial intelligence has focused primarily on listening for radio signals, deliberate transmissions from alien civilizations trying to communicate across the cosmos. Since 1960, when astronomer Frank Drake conducted the first systematic search for alien radio signals in what came to be called Project Ozma, scientists have scanned the sky with increasingly sensitive radio telescopes, hoping to detect patterns in the cosmic static that would indicate intelligent origin. But radio signals represent just one possible technological signature among countless ways that advanced civilizations might make their presence known across interstellar distances. Understanding what intelligent alien technology might reveal means thinking beyond communication attempts to consider the inevitable side effects and engineering projects that any sufficiently advanced civilization would produce. Technology leaves traces. Human civilization has only been producing radio signals for about a century. Yet already, our technological fingerprint extends outward in a sphere over 200 light-years in diameter, expanding at the speed of light. Television broadcasts, radar installations, radio communications. All of this electromagnetic radiation leaks into space, creating a bubble of human-generated signals spreading through the galaxy. An alien civilization with sensitive enough radio telescopes could detect these signals and know that an industrial, technological species exists on Earth, even if we never intentionally try to contact them. Our technology reveals us whether we choose to advertise our presence or not. The same principle applies to alien civilizations. Any technological species using electromagnetic radiation for communication, navigation, or industrial processes would inadvertently create detectable signals. The frequency, pattern, and characteristics of these signals would differ from natural astronomical sources. Natural radio emissions from stars, nebulae, and other cosmic objects tend to be broadband, spread across a wide range of frequencies, or if narrowband, they're produced by specific atomic or molecular transitions at predictable frequencies. Artificial signals, in contrast, might be extremely narrowband, might drift in frequency in patterns that reflect the relative motion of transmitter and receiver, or might contain modulations and patterns that have no natural explanation. The famous WOW signal detected in 1977 by the Big Ear radio telescope at Ohio State University demonstrated what a potential technosignature might look like. For 72 seconds, the telescope received a strong, narrow band signal from the direction of the constellation Sagittarius. The signal was so unusual that astronomer Jerry Amon wrote "Wow" on the printout, giving the detection its name. The signal has never been detected again, despite decades of subsequent observations, and its origin remains unexplained. It might have been terrestrial interference, or a reflection off space debris, or a natural phenomenon we don't yet understand, or it might have been exactly what it appeared to be, a brief, powerful transmission from an alien source that was never repeated. Optical signals represent another detection method. Laser technology on Earth has advanced to the point where powerful lasers could, in principle, outshine the sun at specific wavelengths for brief moments. If we pointed a sufficiently powerful laser at a star, an alien astronomer observing from that star system might detect the flash, recognizing it as artificial because of its extreme brightness at a single wavelength. This is the basis for optical SETI, the search for brief, intense laser pulses from other civilizations. Aliens might use lasers for interstellar communication because lasers are highly directional and can carry large amounts of information. A civilization intentionally trying to contact other species might beam powerful laser pulses toward nearby stars, hoping someone is watching. But some of the most compelling technosignatures might come not from communication attempts, but from large-scale engineering projects. Any advanced civilization would need energy, and energy requirements grow as civilizations become more technologically sophisticated. In 1964, physicist Freeman Dyson proposed that a sufficiently advanced civilization might construct a vast structure around its star to capture a significant fraction of the star's total energy output. This structure, called a Dyson sphere or Dyson swarm, might consist of countless solar panels, habitats, or other components orbiting the star, intercepting sunlight and converting it to useful energy. A complete Dyson sphere would make the star invisible at visible wavelengths. All the light would be absorbed by the structure, but the structure would glow in infrared radiation, emitting the waste heat from whatever processes the captured energy powered. From a distance, a star surrounded by a Dyson sphere would appear anomalously bright in infrared, while being dim or invisible in visible light. Astronomers have searched for such infrared excess stars, cataloguing objects that might be Dyson spheres, though all candidates discovered so far have more mundane explanations like dust clouds or unusual stellar properties. Megastructures don't need to enclose entire stars to be detectable. A single, enormous structure in orbit around a star might block a tiny fraction of the star's light as it passes in front of the star from our perspective. This would create a transit, a dip in the star's brightness, similar to what happens when a planet transits its star. But while planetary transits follow regular, predictable patterns with consistent depths and durations, a megastructure might create irregular, asymmetric transits that don't match any natural explanation. The star KIC 846282, also known as Tabby's star after astronomer Tabitha Boyajian, who led the research team that discovered its unusual behavior, demonstrated what such anomalies might look like. This star, observed by the Kepler Space Telescope, exhibited irregular, dramatic dips in brightness, sometimes dropping by more than 20%, that didn't match the patterns expected from planets, dust clouds, or any other standard astronomical explanation. The irregular timing and unusual shapes of the dimming events led some researchers to speculate about megastructures, though most scientists now favour natural explanations involving dust and debris, possibly from a disintegrating comet or planet. Still, Tabby's star showed that we could detect anomalous dimming patterns, and if megastructures exist, similar observations might reveal them. Atmospheric pollution represents a more subtle, but potentially detectable, technosignature. Industrial civilizations inevitably alter their planet's atmosphere through their activities. On Earth, the Industrial Revolution increased carbon dioxide levels, added artificial chemicals like chlorofluorocarbons, and changed atmospheric chemistry in detectable ways. Some proposed technosignatures involve looking for molecules in exoplanet atmospheres that shouldn't exist naturally. Chlorofluorocarbons, for instance, are entirely artificial. They don't form through natural processes, but are produced industrially. Detecting CFCs in an exoplanet's atmosphere would be strong evidence for industrial activity. Similarly, nitrogen dioxide concentrations above natural levels could indicate industrial combustion. Certain combinations of atmospheric gases might indicate technological activity. For example, large amounts of both oxygen and methane in the same atmosphere shouldn't coexist naturally because these gases react with each other. If both are abundant, something must be continuously producing them. While biology can produce both gases, certain ratios or the presence of specific isotopes might point toward industrial rather than biological sources. City lights offer another potential technosignature. Earth's night side is dramatically brighter than it was before artificial lighting, with cities visible from space as brilliant concentrations of light. An alien civilization observing Earth with sufficiently powerful telescopes could detect this artificial illumination, recognizing it as technological in origin because the light spectrum differs from natural phenomena, like forest fires or volcanic activity. The light would also be concentrated in specific patterns, along coastlines, in networks of roads, around population centers, rather than being randomly distributed. Detecting city lights on exoplanets would be extraordinarily challenging with current technology. The light from the planet's star overwhelms the faint glow of artificial lighting by enormous margins. But future telescopes, particularly those designed to directly image exoplanets by blocking the star's light, might have the sensitivity to detect bright illumination on a planet's night side, especially if the civilization uses inefficient lighting that wastes energy as light escaping into space, rather than being directed downward toward the ground. Space-based infrastructure might be detectable through reflected light or occultations. Satellites, space stations, solar panel arrays, and other orbital structures reflect light from their star. A civilization with extensive orbital infrastructure might create a faint cloud of reflected light around their planet, detectable as excess brightness beyond what the planet itself would reflect. Similarly, Large orbital structures might occasionally pass in front of stars in the background, as seen from Earth, creating very brief, tiny dips in brightness that could be detected through careful monitoring. Propulsion systems represent another potential technosignature. Any civilization attempting interstellar travel would need enormous energy to accelerate spacecraft to significant fractions of light speed. Some proposed propulsion systems would create detectable signatures. Nuclear pulse propulsion, using nuclear explosions for thrust, as proposed in the Orion project, would create distinctive radiation signatures. Antimatter engines would produce gamma rays from matter-antimatter annihilation. Fusion drives would create specific spectral signatures from the fusion reactions. Even laser-pushed light sails, sails accelerated by powerful lasers from the home star system, would create bright laser beams visible across interstellar distances to anyone positioned along the beam's path. Gravitational engineering, if possible, might create detectable anomalies. If advanced civilizations can manipulate gravity or space-time, something beyond our current technological capabilities, but not necessarily forbidden by physics, their activities might create detectable effects. Artificial gravitational waves at unusual frequencies, anomalous motions of stars or planets that suggest artificial manipulation, or regions of space with unexplained gravitational properties could all potentially indicate advanced technology at work. Asteroid mining and large-scale resource extraction would alter the appearance of solar systems. A civilization mining asteroids for raw materials would change the distribution and size of asteroids over time. Spectroscopic observations might reveal unusual compositions in asteroid belts, perhaps unusually low concentrations of useful metals if those metals have been extensively mined. Debris from mining operations might create distinctive dust clouds with unusual properties. Stellar engineering represents the extreme end of technological signatures. Some theorists have proposed that advanced civilizations might manipulate stars themselves, extracting material from stars, changing stellar composition, or even moving stars through space using enormous thrusters. These Shkadov thrusters, named after physicist Leonid Shkadov, would use mirrors or other structures to create thrust from a star's own radiation pressure, allowing the star to be slowly moved over millions of years. A civilization might move their star to escape dangers like nearby supernovae, to position their star system optimally in the galaxy, or to transport their entire solar system on an interstellar journey. A moving star whose motion couldn't be explained by gravitational interactions with other objects might indicate such stellar engineering. Time also factors into detectability. A civilization's technological signatures change as technology evolves. Humanity's radio era might be brief, perhaps only a few centuries between when we developed radio technology and when we transitioned to communication methods that don't leak into space, like fiber optics or directed transmissions. An alien civilization might have a similarly brief radio-loud period. This means that civilizations at different technological stages would produce different signatures. An early industrial civilization might produce atmospheric pollution, but no radio signals. A spacefaring civilization might have extensive orbital infrastructure, but might no longer use radio for communication. An extremely advanced civilization might produce signatures we cannot yet imagine, using technologies and engineering approaches completely beyond our current conceptual framework. The absence of detected technosignatures, despite decades of searching, has led to discussions of the Fermi paradox. If technological civilizations are common, where are their signatures? Perhaps they're too rare or too distant. Perhaps they exist but avoid broadcasting or producing detectable signatures intentionally. Perhaps our detection methods are inadequate or focused on the wrong signatures. Or perhaps advanced civilizations develop technologies that produce no detectable signatures, or signatures we wouldn't recognize because we're not looking for them. What intelligent alien technology might reveal encompasses everything from deliberate messages transmitted across space to the inevitable waste heat and pollution from industrial processes, from the dimming of stars caused by megastructures to the reflected light from orbital infrastructure, from laser flashes used for communication to the gravitational anomalies created by stellar engineering. Each technological signature represents a different window into how civilizations develop, what they value, what problems they solve, and how they reshape their environments. Detecting any of these signatures would answer one of humanity's deepest questions: are we alone? And would provide our first glimpse into how other intelligences have developed technology, overcome challenges, and left their mark on the cosmos, transforming our understanding of what's possible, and revealing that the universe contains not just stars, planets, and lifeless matter, but minds that contemplate the cosmos just as we do, minds that build and create and reach toward the stars. Why alien life might be microscopic. When we imagine alien life, our minds often conjure images of intelligent beings piloting spacecraft, complex organisms with eyes and limbs exploring alien landscapes, or at minimum, creatures we could observe and recognize as alive. But this expectation might be profoundly misguided. Earth's history offers a sobering perspective. For roughly 3 billion of the 4 billion years that life has existed on our planet, all organisms were microscopic. Bacteria, archaea, and single-celled eukaryotes dominated Earth's biosphere for the vast majority of life's history. Complex multicellular organisms, plants, animals, fungi, are recent arrivals, having existed for less than 1 billion years. If Earth's timeline is any indication, most life in the universe might be microscopic, existing as single cells or simple colonies that never evolve into the complex macroscopic forms we're accustomed to seeing. The transition from single-cell to multicellular life represents one of the most difficult evolutionary innovations in Earth's history. It only happened once in the bacterial lineage, never successfully transitioning beyond simple filaments and colonies, and only a few times in the eukaryotic lineage, producing plants, animals, and fungi. This rarity suggests that while single-celled life might emerge relatively easily wherever conditions permit, the evolution of complex multicellularity requires specific circumstances that might not commonly occur. Many alien worlds might develop thriving microbial biospheres that remain forever microscopic because the evolutionary innovations needed for large, complex organisms never occur. Energy availability represents the first major constraint on complexity. Complex multicellular organisms require substantial energy to build and maintain their bodies. They need energy to power specialized organs, to move through their environments, to grow to large sizes. Most of this energy ultimately comes from oxygen-based metabolism, which releases far more energy per molecule of food than anaerobic metabolism does. The efficiency of oxygen metabolism, about 15 times more energetic than the best anaerobic alternatives, enabled the evolution of large active organisms on Earth. But oxygen was not always available in Earth's atmosphere. For the first 2 billion years or more of life's existence, the atmosphere contained very little free oxygen. Life during this time remained entirely microscopic and relatively simple, constrained by the low energy yields of anaerobic metabolism. Only after photosynthetic bacteria evolved and began producing oxygen as a waste product did atmospheric oxygen accumulate, and only after oxygen reached substantial levels could organisms evolve the high-energy metabolisms necessary for large size and complexity. Many alien worlds might never undergo this transition. If photosynthetic life never evolves, or if it evolves but produces different waste products, perhaps using electron donors other than water that don't release oxygen, the atmosphere might remain oxygen poor indefinitely. Life on such worlds would be permanently restricted to anaerobic metabolism, with its inherent energy limitations preventing the evolution of large complex organisms. The biosphere might flourish with countless microscopic species filling every available niche, but nothing larger than perhaps a millimeter would ever evolve, because the energy budgets of anaerobic metabolism cannot support larger sizes or more complex structures. Predation drives much of the evolution toward complexity on Earth. The development of predators created selection pressure for prey to evolve defenses, armor, toxins, multicellularity that makes them too large to be consumed by single-celled predators. Predators, in turn, evolved mechanisms to overcome these defenses: better sensing systems, faster movement, cooperative hunting. This evolutionary arms race between predators and prey drove increasing complexity, with both sides becoming more sophisticated over generations. The transition to multicellularity in animals might have been driven at least partially by predation pressure from other single-celled organisms. On an alien world where predation never becomes significant, perhaps because environmental conditions don't favor the evolution of heterotrophs, or because chemical energy is so abundant that organisms don't need to consume each other, this driver of complexity would be absent. Life might remain a collection of bacteria-like organisms metabolizing chemicals from their environment, with no selection pressure favoring the evolution of larger, more complex forms. Without predation or competition driving an evolutionary arms race, the biosphere might reach an equilibrium of simple, efficient microorganisms that persist unchanged for billions of years. The evolution of eukaryotic cells, cells with nuclei and complex internal structures, required an extraordinarily unlikely event called endosymbiosis, where one cell engulfed another and instead of digesting it, established a permanent symbiotic relationship. On Earth, mitochondria, the energy-producing organelles in eukaryotic cells, originated as free-living bacteria that were engulfed by other cells and eventually became integrated parts of those cells. This event, which happened roughly 2 billion years ago, was apparently unique in Earth's history. It happened once, and all eukaryotic cells descend from that single event. Eukaryotic cells made complex multicellular life possible. Their mitochondria provide far more energy per cell than bacteria can generate, allowing cells to support larger genomes and more complex structures. Their internal compartmentalization allows specialized biochemistry to occur in different cellular regions. Their complex cytoskeletons enable intricate cell shapes and coordinated movements. Without eukaryotic cells, complex multicellular organisms probably could not evolve. If endosymbiosis was difficult, requiring very specific circumstances to occur even once on Earth, alien worlds might never undergo this transition. Life might remain forever bacterial, lacking the cellular complexity necessary as a foundation for multicellular organisms. These worlds would have rich microbial ecosystems with tremendous diversity at the microscopic level, but would never produce organisms visible to the naked eye. Environmental stability influences evolutionary innovation. Earth's environment has been highly variable over geological time. Ice ages, warming periods, asteroid impacts, volcanic catastrophes, changing atmospheric composition, continents drifting and colliding. These environmental changes created selection pressures that favored adaptability and innovation. Mass extinctions wiped out dominant groups, allowing new forms to radiate and diversify. Without such disruptions, dominant organisms might remain unchanged indefinitely, never facing circumstances that favor more complex alternatives. An alien world with a remarkably stable climate and environment over billions of years might never see complex life evolve. Early microbial ecosystems might reach an equilibrium where existing organisms are so well adapted to unchanging conditions that no complex innovations provide advantages. Microbes would efficiently fill every niche, processing every available chemical, extracting every erg of available energy, and no evolutionary pressure would favour the metabolically expensive transition to larger, more complex forms. The planet would remain microbial forever, not because complex life is impossible, but because stable conditions never create circumstances where complexity is advantageous. The availability of ecological niches affects diversification. On Earth, new environmental niches continuously opened as continents drifted, climates changed, and oxygen accumulated in the atmosphere. Moving onto land created entirely new sets of niches, terrestrial environments with different challenges than aquatic ones. Flying created another set of niches. Each new opportunity drove adaptive radiations where organisms evolved to exploit newly available resources and habitats. A planet lacking this niche diversity might not provide opportunities for complex life to evolve. A world completely covered by ocean with no land would lack terrestrial niches. A world with a homogeneous environment, perhaps a global ocean with uniform temperature and chemistry from pole to pole, would offer fewer distinct niches than Earth's highly varied environments. With fewer niches available, there would be less opportunity for adaptive radiation and less selection pressure driving organisms toward the specializations and complexities that fill diverse ecological roles. Timescales matter significantly. Evolution proceeds through random mutations and natural selection, accumulating beneficial changes over countless generations. Complex innovations require many individual evolutionary steps, each one building on previous changes. The evolution of eyes, for instance, required the initial evolution of light-sensitive proteins, then the gathering of these proteins into light-sensitive patches, then the invagination of these patches into cups that provide directional information, then the development of lenses that focus light, then the neural processing systems to interpret visual information. Each step took many generations and many mutations. On an alien world where organisms have very long generation times, perhaps living for thousands of years before reproducing, evolution would proceed extraordinarily slowly. A complex innovation that might evolve in tens of millions of years on Earth, where many organisms reproduce annually or even faster, might take billions of years on a world where generation times are measured in millennia. If the planet star has a relatively short lifetime, perhaps a massive star that will exhaust its fuel in a few billion years, there might simply not be enough time for complex life to evolve before the star's death sterilizes the planet. The chemical environment limits biological complexity. Complex organisms require diverse biochemistry, proteins for structure and catalysis, lipids for membranes, nucleic acids for information storage, carbohydrates for energy and structure. Building these diverse molecules requires access to various elements in appropriate forms. A planet poor in essential elements, perhaps lacking sufficient phosphorus, nitrogen, sulfur, or trace metals, might not provide the chemical building blocks necessary for complex biochemistry. Life might arise using simpler chemistry, but might be unable to evolve the molecular diversity needed for complex cells and multicellular structures. Physical constraints on size affect what complexity is possible. Surface tension becomes increasingly important at small scales. For microscopic organisms living in water, surface tension is a significant force. Water behaves more like thick syrup than like the thin fluid humans experience. Moving through water at microscopic scales requires different strategies than swimming at macroscopic scales. These physical differences mean that microorganisms experience a fundamentally different physical world than large organisms, and the adaptations that work well at microscopic scales might not scale up successfully. The speed of light sets absolute limits on how quickly information can be transmitted within an organism. For microscopic cells, this is never a constraint. Signals cross the cell in negligible time. But as organisms grow larger, signal transmission times become significant. A 1-meter organism experiences light travel times of about 3 nanoseconds, still essentially instantaneous for chemical and neural signals. But organisms must coordinate their parts, and this coordination becomes more difficult as size increases. Neural signals in humans travel at speeds of about 100 meters per second, meaning signals take milliseconds to travel from extremities to brain. For a hypothetical organism many meters or kilometers in size, coordination would become increasingly difficult. Detection bias affects our perception of what life looks like. Humans evolved to perceive objects roughly our own size. We see animals, plants, and landscape features easily because our sensory systems are optimized for that scale. Microscopic organisms are invisible without technological assistance. An alien observer visiting Earth equipped with sensing systems similar to human vision might conclude that Earth has relatively little life, missing entirely the vast microbial world that actually dominates in terms of biomass, diversity, and metabolic activity. Similarly, when we search for alien life, our methods tend to focus on detecting macroscopic effects, oxygen in atmospheres produced by photosynthetic organisms, changes in planetary albedo from vegetation, perhaps even artificial lights from technological civilizations. A planet covered in microbial life, producing no oxygen, with no multicellular organisms, with nothing visible at planetary scales, might appear lifeless to our telescopes, even if it hosts an incredibly rich and diverse microbial biosphere. Statistical considerations based on Earth's history suggest that if we discovered alien life, it would most likely be microscopic. Life existed on Earth for about 3 billion years before complex multicellular organisms evolved. If we randomly selected a moment in Earth's history, there would be a roughly 75% chance of finding only microscopic life. Assuming Earth's timeline is typical, which may or may not be true, most inhabited planets at any given time would be in their microbial phase, with complex life being relatively rare. Why alien life might be microscopic comes down to microbial life being easy to achieve relative to complex life, requiring only basic metabolism, reproduction, and evolution, while complex life requires numerous specific evolutionary innovations, oxygenic photosynthesis or equivalent high-energy metabolism, eukaryotic cells with their mitochondrial endosymbionts, multicellularity with coordinated cells working together, specialized tissues and organs, each one potentially rare or slow to evolve. Many worlds might develop thriving microbial ecosystems within their first billion years, but might never progress beyond that stage, remaining forever inhabited by bacteria-like organisms invisible to the naked eye, yet representing the most common form of life in the universe. A cosmos filled not with civilizations or even visible organisms, but with countless worlds hosting microbial biospheres that flourish in every conceivable environment, from sunlit surface waters to deep subsurface rocks, from hydrothermal vents to subsurface oceans beneath ice, each microscopic cell representing a success story of evolution in its own right, reminding us that complexity and large size are not prerequisites for biological success, and that if we ever detect life beyond Earth, we should not be disappointed if it consists of nothing more than microbes, because microbial life might be life's most common, most successful, most enduring form across the vast expanse of the living universe. Why moons orbit in perfect circles? When you look at diagrams of moons orbiting planets, they're often depicted as perfect circles with the planet at the center. This image is actually misleading. No moon orbits in a perfect circle. Every orbit in the universe, whether it's a moon around a planet around a star, or a star around a galaxy's center, follows an ellipse, a stretched circle with the central body at one of the ellipse's two focal points, not at the center. However, many moon orbits are remarkably close to circular, so nearly circular, that the deviation is barely noticeable. Understanding why some moons have nearly circular orbits, while others follow elongated ellipses, means understanding orbital mechanics, tidal forces, and the long-term evolution of gravitational systems. The fundamental laws governing orbital motion were discovered by Johannes Kepler in the early 17th century, based on meticulous observations of planetary positions compiled by Tycho Brahe. Kepler's first law states that planets orbit the Sun in ellipses, with the Sun at one focus. This applies equally to moons orbiting planets. An ellipse is characterized by its eccentricity, a number between 0 and 1. An eccentricity of 0 represents a perfect circle. An eccentricity close to 0 represents a nearly circular ellipse. Higher eccentricities produce more elongated ellipses, and an eccentricity of 1 represents a parabola, an open curve, not a closed orbit at all. Earth's moon has an orbital eccentricity of about 0.0549, meaning its orbit is quite close to circular but noticeably elliptical. At its closest approach, called perigee, the moon is about 363,000 kilometers from Earth. At its farthest point, called apogee, it's about 405,000 kilometers away, a difference of about 42,000 kilometers, or roughly 11%. This variation causes the moon's apparent size in Earth's sky to change noticeably over the course of a month. A full moon at perigee appears about 14% larger in diameter than a full moon at apogee, the so-called supermoon phenomenon. Many other moons have far more circular orbits than Earth's moon. Jupiter's major moons, the Galilean satellites Io, Europa, Ganymede, and Callisto, all have very low eccentricities. Io's eccentricity is about 0.0041, Europa's is 0.009, Ganymede's is 0.0013, and Callisto's is 0.0074. These are remarkably circular orbits, with the differences between closest and farthest approaches being only tiny fractions of the orbital radius. Saturn's largest moon, Titan, has an eccentricity of 0.0288, still quite circular, though less so than Jupiter's major moons. The reason many moons approach circular orbits lies in tidal forces and the dissipation of energy over time. When a moon orbits a planet on an elliptical path, its distance from the planet changes continuously. As the distance changes, so does the strength of the tidal forces between the planet and moon. Tides work both ways. The moon raises tides on the planet, and the planet raises tides on the moon. These tidal bulges require energy to create because they deform the bodies involved, flexing and stretching them. For a moon in an eccentric orbit, the tidal bulges change in size as the moon moves closer to and farther from the planet. This continuous flexing dissipates energy as heat through internal friction, the same mechanism that makes a rubber ball warm up when you repeatedly squeeze and release it. This tidal heating is not a small effect. Jupiter's moon, Io, experiences such intense tidal heating due to its slightly eccentric orbit that it's the most volcanically active body in the solar system, with lava lakes, erupting volcanoes, and a surface constantly renewed by volcanic activity. The energy dissipated through tidal heating doesn't disappear. It comes from the orbital energy of the moon. As orbital energy is lost, the characteristics of the orbit change. Specifically, the eccentricity decreases. The orbit becomes more circular. This process, called tidal circularization, operates on timescales of millions to billions of years, gradually transforming elliptical orbits into nearly circular ones. The timescale depends on the masses involved, the distances, the physical properties of the bodies, how easily they deform, and the initial eccentricity. Earth's moon provides a clear example of tidal evolution, though in the moon's case the effect is primarily in the exchange of angular momentum rather than circularization. The moon raises tides on Earth, the familiar ocean tides that rise and fall twice daily. Earth's rotation carries these tidal bulges slightly ahead of the Earth-Moon line because of friction and the time it takes for water to respond to the tidal forces. This offset means the tidal bulges pull on the moon, accelerating it in its orbit and causing it to gradually move away from Earth at about 3.8 centimeters per year, a rate precisely measured by bouncing laser beams of retroreflectors left on the moon by Apollo astronauts. As the moon moves outward, Earth's rotation slows down to conserve angular momentum. Earth's day gradually lengthens, currently by about 1.7 milliseconds per century. This process has been operating for billions of years. Early in Earth's history, when the moon was much closer, tidal forces were far stronger. Days were much shorter, perhaps only 5 to 6 hours, and the moon orbited much faster and on a more eccentric orbit. Over billions of years, tidal forces circularized the moon's orbit to its current low, but non-zero eccentricity. The moon's orbital eccentricity isn't zero because the circularization process hasn't completed and perhaps never will. The sun's gravitational pull perturbs the moon's orbit, periodically increasing its eccentricity slightly. These perturbations compete with the tidal circularization, creating a balance that maintains a small but non-zero eccentricity. Additionally, the ultimate end state of tidal evolution is tidal locking, where the moon always shows the same face to the planet, and the planet's rotation period equals the moon's orbital period. Earth's moon is already tidally locked to Earth, but Earth is not locked to the moon. Eventually, if given enough time, Earth would become locked to the moon as well, with both bodies always showing the same faces to each other. Though this would take tens of billions of years, longer than the sun's remaining lifetime. Some moons maintain eccentric orbits despite tidal forces because of orbital resonances with other moons. Jupiter's moons Io, Europa, and Ganymede are locked in a 1 to 2 to 4 resonance. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This resonance was discovered by Pierre-Simon Laplace in the 18th century. The gravitational interactions in this resonance maintain Io's and Europa's orbital eccentricities even as tidal forces try to circularize them. The result is continuous tidal heating, keeping Io's interior molten and likely maintaining a subsurface ocean on Europa beneath its icy crust. Saturn's moon Enceladus experiences similar effects. Its orbital eccentricity of about 0.0047 seems small, but it's sufficient to generate significant tidal heating in this small moon. Enceladus orbits in a 2 to 1 resonance with the larger moon Dione. The resonance prevents the orbit from fully circularizing, maintaining just enough eccentricity to produce tidal heating that keeps a subsurface ocean liquid beneath Enceladus's southern polar region. Geysers of water erupt through cracks in the ice, spraying material into space and creating Saturn's E-ring. New moons in eccentric orbits take time to circularize. If a moon forms from a giant impact, as Earth's moon likely did, the debris initially orbits in highly eccentric, chaotic paths. Over time, collisions between orbiting fragments dissipate energy and circularize the orbits, while material gradually coalesces into a single moon. The moon starts with a moderately eccentric orbit that gradually becomes more circular through tidal interactions. Young moons should have more eccentric orbits than old moons, all else being equal. Captured moons often retain eccentric orbits. When a planet gravitationally captures a passing asteroid or comet, the capture typically results in a highly eccentric orbit. Without significant tidal forces or atmospheric drag to circularize the orbit, it remains eccentric indefinitely. This is why many of the small, irregular outer moons of the giant planets have highly eccentric orbits. Their captured asteroids, or Kuiper belt objects that have never undergone significant tidal circularization. Mars's two small moons, Phobos and Deimos, are thought to be captured asteroids, though their orbits are fairly circular, suggesting either that they've been in place long enough for tides to act or that they were captured through an unusual mechanism that placed them in nearly circular orbits initially. The mathematical framework for understanding orbital evolution through tides was developed in the 19th and 20th centuries by George Darwin, son of Charles Darwin, and others. The tidal quality factor, denoted Q, quantifies how efficiently a body dissipates tidal energy. Bodies with low Q dissipate energy efficiently, leading to faster orbital evolution. Rocky bodies typically have Q values of 10 to 100. Gas giants have Q values around 10,000 to 100,000 because gases don't maintain permanent tidal bulges as efficiently as solid or liquid bodies. These Q values determine how quickly orbits evolve. Computer simulations of moon system evolution incorporate tidal effects, gravitational interactions between multiple moons, and perturbations from the Sun and other planets. These simulations show that systems naturally evolve toward configurations with circular orbits, tidal locking, and often orbital resonances. The solar system's moon systems we observe today represent billions of years of this evolution, with orbits that have circularized, resonances that have captured moons into stable configurations, and tidal locking that has synchronized rotations. Some moons will never fully circularize their orbits because external perturbations constantly act to increase eccentricity. The moon's orbit around Earth is perturbed by the Sun, creating periodic variations in eccentricity over 27.5-day cycles. Neptune's moon Triton orbits in a retrograde direction, opposite to Neptune's rotation, suggesting it was captured from the Kuiper belt. Triton's orbit has circularized over billions of years to an eccentricity of only 0.000016, one of the most circular orbits known, but the orbit is also slowly decaying. Tidal forces are causing Triton to spiral inward, and in about 3.6 billion years, it will cross Neptune's Roche limit and be torn apart, forming a spectacular ring system. The appearance of circular orbits in diagrams and popular depictions stems from the fact that many major moons genuinely have nearly circular orbits. Eccentricities low enough that drawing the ellipse versus a circle would show barely any difference. For Ganymede, with its eccentricity of 0.0013, the difference between the orbit's longest and shortest diameters is only 0.26%. Drawing this accurately would require extraordinary precision. For practical purposes, these orbits are functionally circular, even though they're technically ellipses. Perfect circles don't exist in orbital mechanics because achieving exactly zero eccentricity requires perfectly balanced initial conditions and no subsequent perturbations, conditions that never occur in nature. But through billions of years of tidal evolution, many moons have achieved orbits so close to circular that they serve as excellent approximations shaped by the patient, inexorable work of tidal forces, dissipating energy, transforming the chaos of formation into the elegant, nearly circular orbits that characterize mature moon systems throughout the solar system, demonstrating how gravitational interactions over immense timescales can organize and simplify what begins as disorder, creating the stable, predictable, celestial mechanics that allow us to calculate moon positions years or centuries into the future with extraordinary precision. Why some asteroids are made of metal? Most asteroids are dark, rocky bodies composed of silicate minerals similar to the rocks found on Earth's surface. But among the hundreds of thousands of asteroids orbiting in the main belt between Mars and Jupiter, a small population stands out as fundamentally different. These are the metallic asteroids, composed primarily of iron and nickel rather than rock. They gleam brightly in reflected sunlight. their surfaces shining with the luster of exposed metal. The most famous of these is Psyche, a massive asteroid about 226 kilometers in diameter that appears to be almost entirely metallic. Understanding why some asteroids are made of metal means understanding the violent history of the early solar system and the process by which planets form their layered structures of core, mantle, and crust. The story of metallic asteroids begins with planetary differentiation, the process by which a planetary body separates into layers based on density. When a planet or large asteroid forms, it starts as a mixture of materials, rock-forming elements like silicon, oxygen, magnesium, and calcium mixed with metallic elements like iron and nickel. If the body grows large enough and contains enough radioactive elements, it heats up from the decay of radioactive isotopes and from the energy of continued impacts as it accretes more material. When the temperature rises above the melting point of iron, about 1538 degrees Celsius, something dramatic happens. The iron, being denser than the surrounding silicate rock, begins to sink toward the center of the body. This process, called the iron catastrophe, releases enormous amounts of gravitational potential energy as the dense metal falls inward, further heating the body. The result is a differentiated structure with a dense iron-nickel core at the center, surrounded by a rocky mantle of lighter silicate minerals, and potentially a thin crust at the surface. This is the same basic structure that Earth possesses, an iron-nickel core containing about 32% of Earth's mass, surrounded by a silicate mantle and crust. Planetary differentiation occurred in the early solar system in bodies large enough to melt their interiors. Earth differentiated, Mars differentiated, Venus almost certainly differentiated. Even some large asteroids, like Vesta, which has a diameter of about 525 kilometers, underwent differentiation. Vesta has a basaltic crust formed from volcanic activity, indicating that it once had a molten interior with a metallic core. The asteroid Ceres, the largest object in the asteroid belt, at about 940 kilometers in diameter, shows evidence of differentiation as well. Once a body has differentiated into core, mantle, and crust, it becomes vulnerable to catastrophic disruption. The early solar system was a chaotic place, filled with planetesimals, asteroid-sized objects, colliding frequently as they orbited the young sun. Computer simulations of this period show that collisions were not just common, but inevitable. Some collisions led to accretion, with two bodies merging to form a larger one, but others were catastrophically disruptive, shattering one or both bodies into fragments. When a differentiated planetesimal is shattered by a sufficiently energetic collision, the fragments don't all have the same composition. Pieces from the core are metallic, pieces from the mantle are rocky, pieces from the crust might be volcanic basalts if the body had volcanism. These fragments become separate asteroids, each one representing a sample of a specific layer from the parent body. This is why we find three distinct types of asteroids in the main belt: C-type asteroids, which are carbonaceous and primitive, never having melted; S-type asteroids, which are stony and represent crustal and mantle material; and M-type asteroids, which are metallic and represent exposed cores. The M-type designation comes from their metallic composition, though determining composition from Earth requires spectroscopic analysis and radar observations. M-type asteroids are typically much more reflective than rocky asteroids. Their albedo, or reflectivity, ranges from about 10 to 18%, compared to 3 to 7% for dark carbonaceous asteroids. This high reflectivity occurs because metal reflects light efficiently compared to dark silicate minerals. The spectroscopic signatures of M-type asteroids show features consistent with iron and nickel, though definitively confirming their composition requires spacecraft missions or detailed radar studies. Radar observations provide particularly strong evidence for the metallic nature of M-type asteroids. Radio waves reflect differently from metal surfaces than from rocky surfaces. Metal is a much better radar reflector, and radar polarization measurements can distinguish metallic from rocky compositions. Studies using the Arecibo Observatory and Goldstone Solar System radar have confirmed that many M-type asteroids have radar properties consistent with metallic surfaces, supporting the interpretation that they're exposed planetary cores. The asteroid Psyche represents the most studied example of a metallic asteroid and the target of NASA's Psyche mission, launched in 2023 and scheduled to arrive at the asteroid in 2029. Psyche is unusual even among M-type asteroids because of its enormous size and apparently high metal content. If Psyche is indeed the exposed core of a differentiated planetesimal, it would be the only core of a planetary body that humans have ever been able to study directly. Earth's core lies 2,900 kilometers beneath the surface, completely inaccessible. Mars's core is similarly hidden, but Psyche's core is exposed, available for investigation. The composition of metallic asteroids reflects the composition of planetary cores more generally. Iron and nickel are the dominant elements, present in roughly the same proportions found in iron meteorites that fall to Earth, about 90% iron and 10% nickel, though with some variation. These proportions match what cosmochemical models predict for the cores of terrestrial planets. Additional elements found in smaller quantities include cobalt, phosphorus, sulfur, and carbon. Some models suggest that planetary cores might contain significant amounts of lighter elements, like silicon or oxygen, dissolved in the molten metal, but whether these would be retained in a fragmented, solidified core like Psyche remains uncertain. The value of metallic asteroids extends beyond scientific interest. These asteroids contain enormous quantities of valuable metals. A single metallic asteroid a kilometer across might contain more platinum group metals than have ever been mined on Earth. The asteroid 16 Psyche, if it's as metallic as estimates suggest, would contain iron alone worth quadrillions of dollars at current prices, though of course actually mining and returning such quantities would crash commodity markets and is far beyond current technological capabilities. Nevertheless, the concept of asteroid mining has captured imaginations and may become economically viable in the future as space access costs decrease and in-space manufacturing develops. Not all M-type asteroids are metallic, which complicates the picture. Some asteroids classified as M-type, based on their reflectivity and spectroscopic properties, might actually be enstatite chondrites, a rare type of rocky meteorites with high reflectivity, or other unusual rock types that mimic the appearance of metal. This demonstrates the difficulty of determining asteroid composition remotely. Only with spacecraft missions, sample return, or eventually human exploration can we definitively establish what these objects are made of. The formation of metallic asteroids also constrains the timing and locations of planet formation in the early solar system. Differentiation requires heating, which comes primarily from radioactive decay of short-lived isotopes like aluminum-26, which has a half-life of only 717,000 years. For aluminum-26 to provide significant heating, the planetesimal must form within a few million years of the solar system's birth, while aluminum-26 is still abundant. This timing constraint suggests that the parent bodies of metallic asteroids formed quickly within the first few million years of solar system history. The subsequent disruption of these differentiated bodies likely occurred during a period of intense bombardment, possibly associated with dynamical instabilities in the giant planet's orbits. The Nice model, named after the city in France where it was developed, proposes that Jupiter, Saturn, Uranus, and Neptune formed in a more compact configuration and later migrated to their current orbits. This migration scattered planetesimals throughout the solar system, dramatically increasing collision rates and leading to the disruption of many differentiated bodies. The timing of this instability, estimated at around 600 to 800 million years after the solar system formed, would have been late enough for the large planetesimals to have already cooled and solidified after their differentiation. Iron meteorites that fall to Earth are fragments of metallic asteroids, providing samples we can study in laboratories. These meteorites show distinctive crystalline structures called Widmanstätten patterns, interlocking crystals of two different iron-nickel alloys, camosite and taenite, that form only when molten metal cools extremely slowly over millions of years. The size and structure of these crystals reveal the cooling history of the parent body's core. Some iron meteorites cooled at rates of only a few degrees Celsius per million years, consistent with cooling in the interior of a body tens to hundreds of kilometers in diameter, exactly the size of the differentiated planetesimals that became the parent bodies of metallic asteroids. The Widmanstätten patterns become visible when iron meteorites are cut, polished and etched with acid. The two iron-nickel alloys etch at different rates, revealing the crystalline structure. These patterns are beautiful and distinctive, and they can only form under the pressure and temperature conditions found deep within planetary cores, providing strong evidence that iron meteorites, and by extension metallic asteroids, genuinely represent fragments of ancient planetary cores. The distribution of metallic asteroids in the asteroid belt provides additional clues about the formation and evolution of the solar system. M-type asteroids are found throughout the main belt, but are somewhat more common in the middle regions. This distribution might reflect where conditions were favourable for forming large, differentiated planetesimals, and where subsequent collisions occurred that could disrupt them. The relative scarcity of metallic asteroids compared to rocky ones, M-types represent only about 5 to 10% of asteroids, makes sense given that a differentiated body's core contains much less volume than its mantle and crust combined. Some metallic asteroids might not be fragments of differentiated bodies at all, but could have formed through different processes. Certain types of impactors, if they struck at very high velocities, could strip away a body's mantle and crust while leaving the core relatively intact. Alternatively, some metal-rich asteroids might have formed from material that was already enriched in metals during the solar system's formation, though this seems less likely given what we know about how materials were distributed in the protoplanetary disk. The Psyche mission will answer many questions about metallic asteroids when it arrives at its target. The spacecraft will map Psyche's surface in detail, measure its gravity field to determine how mass is distributed internally, study its magnetic properties to search for evidence of an ancient magnetic field that might have existed when the core was still molten, and analyze its composition using spectrometers and cameras. These measurements will reveal whether Psyche is indeed a nearly pure metallic core, as many scientists suspect, or whether it has a more complex structure with rock mixed in or covering parts of the surface. Understanding metallic asteroids means understanding planetary cores, the process of differentiation, the violence of the early solar system, and the building blocks from which planets formed. Every metallic asteroid is a window into planetary interiors, exposing material that would otherwise remain forever hidden beneath thousands of kilometers of rock. These fragments of ancient cores, forged in the heat of differentiation and revealed by catastrophic collisions, represent some of the oldest processed materials in the solar system. Samples of the massive bodies that either grew into planets or were destroyed in the chaos of planetary formation, leaving behind their metallic hearts orbiting the sun as testament to the violent processes that shaped our cosmic neighborhood billions of years ago. Why space looks black? When astronauts look out the windows of the International Space Station, they see a view that never fails to inspire awe. Earth below with its blue oceans and swirling white clouds, and beyond it, the blackness of space dotted with brilliant points of starlight. That darkness seems natural and expected. Space is far from the sun, far from Earth's atmosphere, so of course it's dark. But this simple explanation masks a puzzle that perplexed astronomers for centuries. If the universe is infinite and filled with stars in every direction, then no matter where you look, your line of sight should eventually hit a star. The entire sky should blaze with light, as bright as the surface of the sun in every direction. Yet space is dark. This contradiction, known as Olbers' paradox after the German astronomer who popularized it in the 19th century, reveals deep truths about the universe's nature, age, and evolution. The puzzle seemed straightforward to early astronomers. Imagine the universe extends forever in all directions, filled uniformly with stars. Draw an imaginary sphere around Earth at any distance. That sphere contains a certain number of stars. Now draw a larger sphere at twice the distance. This larger sphere has 4 times the surface area, so it contains 4 times as many stars. Each individual star appears fainter because it's farther away. Brightness decreases with the square of distance, but there are 4 times as many stars, exactly compensating for their individual faintness. Every shell at every distance contributes the same amount of light. If the universe is infinite, there are infinitely many such shells, so the total light should be infinite. The night sky should be blindingly bright. Clearly, this doesn't match what we observe. The night sky is dark except for individual stars, planets, and the faint band of the Milky Way. Something must be wrong with the reasoning. Early astronomers proposed various solutions. Perhaps dust between stars absorbs starlight, darkening distant regions. But this doesn't really solve the problem. The dust would heat up from absorbed starlight and would eventually glow just as brightly as the stars themselves. Perhaps stars aren't distributed uniformly, with empty voids creating dark patches. But if the universe is infinite and eternal, stars should exist everywhere eventually, filling in any voids given enough time. The true solution involves the universe's finite age and its expansion, concepts unknown when Olbers formulated his paradox. The universe is not infinitely old. It began roughly 14 billion years ago in the Big Bang. Light travels at a finite speed, so we can only see light from objects whose light has had time to reach us since the universe began. The observable universe has a boundary, not a physical edge, but a horizon beyond which we cannot see, because light from more distant regions hasn't had enough time to reach us yet. This finite light travel time alone would solve Olbers' paradox, even if the universe weren't expanding. There simply aren't infinitely many stars visible, only those within about 14 billion light-years, the distance light can travel in the age of the universe. This limits the total amount of starlight reaching us to a finite value, much less than would be needed to make the sky bright everywhere. But the universe's expansion adds another crucial element. Distant galaxies are receding from us as space itself expands. This recession causes their light to be redshifted, stretched to longer wavelengths. Light that left a distant galaxy as visible or ultraviolet radiation arrives, at Earth shifted into infrared or even microwave wavelengths. Our eyes cannot detect infrared or microwave light, so this redshifted radiation doesn't contribute to the visible brightness of the sky. The farther away a galaxy is, the faster it's receding, and the more severely its light is redshifted. The most distant galaxies we can observe have their visible light redshifted so far that it arrives as infrared or even radio waves. The cosmic microwave background radiation demonstrates this effect perfectly. This radiation, released when the universe was only about 380,000 years old, fills all of space uniformly. When it was emitted, it was visible an infrared light with a temperature of about 3,000 degrees. But in the billions of years since then, the universe has expanded by a factor of about 1,100. The wavelengths of this radiation have been stretched by the same factor, shifting what was once visible light into microwave wavelengths. The temperature corresponding to this radiation has dropped to less than 3 degrees above absolute zero. If we had eyes that could see microwaves, the sky would glow uniformly in every direction with this faint microwave light. But in visible light, it contributes nothing, leaving the sky dark. Another factor contributing to the darkness of space is the finite lifespan of stars and galaxies in their current bright state. Stars don't shine forever. They exhaust their fuel and fade. The universe's star formation rate was higher in the past and is declining now as gas is used up. In the far future, the universe will contain many more dead stellar remnants than active shining stars. Even if the universe were infinitely old, which it isn't, the sky might still be dark because most stars would have long since burned out. The darkness also depends on perspective. From Earth's surface, the atmosphere scatters sunlight, making the daytime sky bright blue and the nighttime sky somewhat illuminated by air glow and scattered artificial light. In space, without atmosphere to scatter light, the sky appears black in all directions, except where you're looking directly at a light source. Sunlight doesn't fill space with general brightness the way it illuminates Earth's atmosphere. Light travels in straight lines, and unless it's scattered or reflected by something, it remains invisible. You can be in bright sunlight in space, with the sun illuminating your spacecraft, but when you look away from the sun, you see only darkness and stars. The blackness of space also reveals something about the nature of light and vision. We see objects because they emit or reflect light into our eyes. Empty space contains no particles to scatter or reflect light, so there's nothing to see. It appears black. This is different from looking into a dark room on Earth, where at least some scattered light usually reveals dim shapes. Space between stars is truly empty of matter, with typically less than 1 atom per cubic centimetre. With so few particles to interact with light, the light simply passes through unaffected, leaving space black. Interstellar dust does exist, and it does affect starlight, but not enough to solve Olber's paradox. The dust absorbs and scatters light from stars behind it, causing extinction, making those stars appear fainter or invisible. This creates the dark dust lanes visible in photographs of the Milky Way and other galaxies. But the dust also glows faintly in infrared light from absorbed stellar radiation. The net effect is to redistribute light from visible to infrared wavelengths, not to eliminate it entirely. Even in regions with many visible stars, the spaces between them remain black. The Orion Nebula, one of the brightest nebulae visible to the naked eye, appears as a glowing cloud because gas in the nebula fluoresces in response to ultraviolet light from young hot stars within it. The gas absorbs ultraviolet light and re-emits it as visible light, making the nebula glow. But between the glowing gas clouds, space remains dark. Only where matter exists to interact with light does the light become visible. From certain perspectives, space isn't quite black. Sensitive instruments can detect faint glows from various sources. Zodiacal light, caused by sunlight reflecting off dust particles in the inner solar system, creates a faint glow along the ecliptic. Airglow from Earth's upper atmosphere creates a faint luminescence visible from orbit. The integrated starlight from billions of faint, unresolved stars creates a faint background glow called the extragalactic background light. But these glows are extraordinarily faint, thousands of times dimmer than the darkest sky visible from Earth's surface, and our eyes cannot detect them. To human vision, space appears black. The darkness of space has practical implications for astronomy. Because space is black, stars and other objects stand out clearly against the background without competing light washing them out. The best ground-based telescopes are built on remote mountaintops, far from city lights, precisely to take advantage of darker skies. But even the darkest Earth-based site cannot match the blackness of space. where no atmosphere scatters light, and where the sky is dark even in the direction of the sun. This darkness also affects spacecraft and astronaut safety. On the shadowed side of Earth or another planet, or in the shadow of the spacecraft itself, darkness is absolute, except for starlight. Astronauts working in shadow must use artificial lights because the starlight alone is far too faint to see by. The contrast between brilliant sunlight and deep shadow is extreme, creating challenges for cameras and human eyes trying to see details in both bright and dark areas simultaneously. The question of why space looks black connects to the deepest questions about the universe's structure and history. Space is dark because the universe had a beginning, because it's expanding, because light travels at a finite speed, and because stars have finite lifetimes. If any of these factors were different, if the universe were infinitely old and static, for instance, the sky would not be dark. The darkness itself is evidence for the Big Bang, for cosmic expansion, for the finite age of the universe. Every time you look up at the night sky and see darkness punctuated by stars rather than a uniform blaze of light, you're seeing direct evidence that the universe had a beginning, that it's been expanding for billions of years, stretching the light from distant sources into wavelengths your eyes cannot detect, leaving the spaces between stars as dark voids that reveal the fundamental nature of the cosmos through their very emptiness. How black holes warp time itself. Time is not the constant, uniform flow that our everyday experience suggests. It can stretch, compress, and slow down, depending on the gravitational environment you're in. Nowhere is this more extreme than near a black hole, where gravity becomes so intense that time itself warps, in ways that challenge our intuition and transform our understanding of reality. Understanding how black holes affect time means grappling with one of the most profound insights of modern physics, that space and time are not separate, fixed stages on which events unfold, but rather a unified fabric that can be bent, twisted, and stretched by the presence of mass and energy. The foundation for understanding time dilation near black holes comes from Albert Einstein's general theory of relativity, published in 1915. Einstein proposed that what we perceive as gravity is actually the curvature of spacetime caused by mass and energy. Massive objects create depressions in the fabric of spacetime, much like a bowling ball placed on a stretched rubber sheet creates a depression that affects how nearby marbles roll. This curvature affects not just the paths that objects follow through space, but also the rate at which time passes. The basic principle is that time passes more slowly in stronger gravitational fields. This effect, called gravitational time dilation, has been confirmed through countless experiments. Atomic clocks placed at different altitudes on Earth tick at measurably different rates. Clocks at sea level run slightly slower than clocks on mountaintops, because they're deeper in Earth's gravitational well. The difference is tiny, only nanoseconds per day, but it's real and measurable. GPS satellites must account for this effect. Without corrections for gravitational time dilation, GPS coordinates would drift by several kilometers per day. Near a black hole, gravitational time dilation becomes extreme. Imagine two observers, one hovering far from a black hole in weak gravity, the other hovering closer to the black hole, where gravity is much stronger. If both observers synchronize their watches and then separate, the watch closer to the black hole will tick more slowly from the distant observer's perspective. This isn't an illusion or a malfunction of the watch. Time genuinely passes more slowly in the stronger gravitational field. The closer you get to a black hole, the more severe this effect becomes. At the event horizon, the boundary beyond which nothing can escape, time dilation becomes infinite from the perspective of a distant observer. This creates one of the most counterintuitive aspects of black holes. If you were to watch someone fall toward a black hole while you remained safely far away, you would see something strange. As the falling person approached the event horizon, they would appear to slow down. Their movements would become sluggish, their signals would take longer to reach you, and their image would become increasingly red-shifted as the light they emit is stretched by the intense gravity. From your distant vantage point, the falling person would never quite seem to cross the event horizon. They would appear to freeze at the boundary, becoming dimmer and redder until they faded from view entirely. This isn't because they stopped falling. From their own perspective, they would cross the event horizon and continue falling inward in a finite amount of time, experiencing nothing unusual at that precise moment. The difference is entirely due to how time flows differently in different gravitational fields. This discrepancy between what the falling observer experiences and what the distant observer sees is one of the most mind-bending aspects of general relativity. Both perspectives are equally valid. The falling observer crosses the event horizon in, say, 10 seconds by their clock, but from the distant observer's perspective, watching that crossing would take infinite time. It would never be complete. This isn't a contradiction, but rather a demonstration that time is not absolute. Different observers in different gravitational fields experience time at different rates. The mathematics describing this time dilation near black holes was first worked out by Carl Schwarzschild in 1916, just months after Einstein published general relativity. Schwarzschild found an exact solution to Einstein's equations describing the spacetime around a non-rotating, spherically symmetric mass, what we now call a Schwarzschild black hole. His solution showed that time dilation increases as you approach the event horizon, located at what's now called the Schwarzschild radius, reaching infinite dilation exactly at the horizon. For a rotating black hole, described by the Kerr solution, found by Roy Kerr in 1963, the situation becomes even more complex. Rotation creates additional effects beyond simple time dilation. The black hole drags spacetime around with it in a process called frame dragging. Close to a rotating black hole, space itself is pulled around in the direction of rotation. You couldn't remain stationary even if you wanted to. You'd be forced to rotate with the spacetime itself. This creates regions like the ergosphere outside the event horizon, where frame dragging is so strong that everything must move in the direction of the black hole's rotation. The warping of time near black holes has practical implications for anything orbiting or falling toward them. Consider material in an accretion disk spiraling into a black hole. Material in the inner portions of the disk closer to the black hole experiences stronger time dilation than material farther out. From the perspective of an observer far from the black hole, processes in the inner disk appear to run in slow motion compared to processes in the outer disk. This affects how we observe black holes and interpret the light we receive from matter near them. Time dilation also affects the gravitational redshift of light, escaping from near a black hole. Light climbing out of a gravitational well loses energy, its wavelength stretching toward the red end of the spectrum. This gravitational redshift is intimately connected to time dilation. They're two aspects of the same phenomenon. A photon emitted from close to the event horizon will be dramatically redshifted by the time it reaches a distant observer. If the photon is emitted from the event horizon itself, it would be redshifted infinitely, its energy dropping to zero, another way of understanding why nothing can escape from beyond the horizon. Inside the event horizon, the warping of spacetime becomes even more extreme. In this region, the roles of space and time actually exchange in a sense. Outside the horizon, moving forward in time is inevitable. You cannot choose to move backward in time, but you can choose your direction in space. Inside the horizon, moving toward the singularity at the center becomes as inevitable as moving forward in time outside the horizon. All possible paths lead inward, and reaching the singularity becomes as unavoidable as reaching the next moment in time. The singularity at the center of a black hole represents a place where space-time curvature becomes infinite, and general relativity's equations break down. At the singularity, time itself becomes undefined in the classical sense. This suggests that general relativity is incomplete, that a theory of quantum gravity would be needed to properly describe what happens at and beyond the singularity. String theory, loop quantum gravity, and other approaches to quantum gravity propose different solutions to what occurs at this extreme limit, but none have been confirmed experimentally. Supermassive black holes at the centers of galaxies create fascinating time dilation effects on galactic scales. The black hole at the center of our Milky Way galaxy, called Sagittarius A star, contains about 4 million solar masses. Stars orbiting close to this black hole experience measurable time dilation. A star in a close orbit around Sagittarius A star, coming within a few hundred times the black hole's event horizon radius, would experience time flowing noticeably slower than we experience it here on Earth, 26,000 light-years away. Precise measurements of these stars' orbits by Andrea Ghez and Reinhard Genzel, who shared the 2020 Nobel Prize in Physics for this work, have confirmed general relativity's predictions in this strong gravity regime. Time dilation near black holes has captured popular imagination, featuring prominently in science fiction. The film Interstellar depicted a planet orbiting close to a massive rotating black hole, where time dilation was so extreme that 1 hour on the planet's surface equaled 7 years of time passing elsewhere. While Hollywood took some liberties, the basic physics was sound. Physicist Kip Thorne served as scientific consultant and later published papers about the black hole physics portrayed in the film. Such extreme time dilation is theoretically possible near a rapidly rotating supermassive black hole. Binary black hole systems, where two black holes orbit each other before merging, create incredibly complex spacetime geometries. Each black hole warps time in its vicinity, and the combined warping creates regions where time flows at different rates depending on your location relative to the two black holes. As the black holes spiral together and merge, events that produce the gravitational waves detected by LIGO and other observatories, the warping of spacetime becomes dynamical, with gravitational waves carrying information about how spacetime is oscillating and rippling during this violent event. The connection between time dilation and energy offers another perspective on these phenomena. According to general relativity, gravitational fields contain energy. A clock deep in a gravitational well, where time runs slowly, can be thought of as having less energy than a clock far from any gravitational source. The gravitational redshift of light, the loss of energy as light climbs out of a gravitational well, reflects this energy difference between different regions of curved spacetime. Black holes also raise profound questions about the nature of time itself. Some interpretations of quantum mechanics and general relativity suggest that time might not be fundamental, but rather an emergent property of more basic physical processes. Black holes, where classical notions of time break down at the singularity, might provide clues about the true nature of time. The information paradox, the question of what happens to information that falls into a black hole, connects to deep questions about time, entropy, and the quantum nature of spacetime. Hawking radiation, predicted by Stephen Hawking in 1974, introduces another connection between black holes and time. Quantum effects near the event horizon cause black holes to emit radiation and slowly evaporate over extremely long timescales. This process involves virtual particle pairs appearing near the horizon, with one particle falling in while the other escapes. The evaporation means black holes have a finite lifetime, and it connects quantum mechanics, gravity, and thermodynamics in ways that hint at a deeper theory unifying these domains. The warping of time near black holes is not science fiction, but established physics, confirmed through observations and experiments. Every time LIGO detects gravitational waves from merging black holes, it's detecting ripples in space-time that carry information about how dramatically space-time, and therefore time itself, was warped during the merger. Every observation of matter orbiting near black holes, every measurement of gravitational redshift, every test of general relativity in strong gravitational fields confirms that time is not absolute, but is woven into the fabric of space-time, susceptible to warping and stretching by mass and energy, reaching its most extreme manifestation near black holes, where the flow of time slows to a crawl, and ultimately, at the event horizon, appears to stop entirely from the perspective of distant observers watching the inexorable pull of gravity on the fabric of reality itself. How galaxies live and die. Galaxies are not eternal, unchanging structures frozen in the void. They are dynamic systems that evolve over billions of years, passing through distinct phases from birth to maturity to eventual decline. Each galaxy follows a life story shaped by gravity, star formation, gas flows, and violent interactions with other galaxies, ultimately transforming from active star-forming systems into quiet collections of aging stars, or sometimes meeting more dramatic fates in collisions that tear them apart and rebuild them into something new. The birth of a galaxy begins in the early universe, just a few 100 million years after the Big Bang. At this time, the cosmos was filled with vast clouds of hydrogen and helium, distributed nearly uniformly, but with tiny variations in density imprinted during the first moments after the Big Bang. Dark matter, invisible but gravitationally powerful, began to collapse first into clumps and filaments, creating gravitational wells that attracted normal matter. Gas flowed along these dark matter filaments, accumulating in regions where the gravitational pull was strongest. These early accumulations of gas were turbulent, chaotic places. The gas was cold, collapsing under its own gravity into smaller and smaller clumps. Within these collapsing clouds, the first stars ignited, massive and brilliant, burning through their nuclear fuel in just a few million years before exploding as supernova. These explosions enriched the surrounding gas with heavier elements, carbon, oxygen, iron, and others, that hadn't existed in the primordial universe. More stars formed from this enriched gas, creating a positive feedback cycle where star formation bred more star formation. A young galaxy is a vigorous place, forming stars at prodigious rates. Gas continues to fall into the galaxy from the surrounding cosmic web, providing fresh fuel for star formation. These early galaxies are often irregular in shape, lacking the elegant spiral arms or smooth elliptical forms of mature galaxies. They're clumpy and asymmetric, filled with giant regions of intense star formation where thousands of stars are being born simultaneously. The massive stars in these regions produce copious ultraviolet radiation that ionizes the surrounding gas, creating glowing nebulae visible across vast distances. As a galaxy matures, it begins to develop structure. If it has significant angular momentum, inherited from the rotation of the gas cloud from which it formed, it settles into a rotating disk. Within this disk, density waves organize stars and gas into spiral arms, elegant patterns that rotate around the galactic center. Stars form preferentially in these spiral arms, where gas is compressed by the passing density wave. The galaxy takes on the classic spiral form we see in galaxies like our own Milky Way or the nearby Andromeda galaxy. The disk of a spiral galaxy contains young hot blue stars mixed with older, cooler yellow and red stars. Gas lanes trace the spiral arms, visible as dark patches where dust blocks light from stars behind. At the center lies the bulge, a roughly spherical concentration of older stars, and at the very heart of the bulge lurks a supermassive black hole, containing millions to billions of times the mass of the Sun. This black hole profoundly influences the galaxy's evolution, though in ways that are still not completely understood. Star formation in a mature galaxy is a self-regulating process. Gas collapses to form stars, but the stars themselves affect the gas around them. Massive stars produce powerful winds that push gas away. Supernova explosions inject tremendous energy into the interstellar medium, heating gas and driving it outward in expanding bubbles and shells. This feedback can temporarily suppress star formation in regions around young star clusters, giving the galaxy a breathing, pulsating quality where star formation surges and ebbs over millions of years. The supermassive black hole at a galaxy's center can dramatically affect its evolution. When gas falls toward the black hole, it forms an accretion disk, heating to millions of degrees and emitting intense radiation across the electromagnetic spectrum. This active galactic nucleus can outshine all the stars in the galaxy combined. The energy released can drive powerful winds and jets that blow gas out of the galaxy entirely, removing the raw material needed for star formation. Many galaxies go through active phases when their central black holes are feeding vigorously, then quiet phases when little material is falling inward and the black hole lies dormant. Galaxies don't evolve in isolation. They're part of a cosmic web, connected by filaments of dark matter and gas to other galaxies nearby. Smaller galaxies fall into larger ones, adding their stars and gas to the growing giant. The Milky Way has consumed dozens of smaller satellite galaxies over its history, and it will consume more in the future. Each merger adds complexity to the galaxy's structure, sometimes triggering bursts of star formation as gas clouds collide and compress, sometimes disrupting the orderly rotation of the disk and scattering stars into less organized orbits. Major mergers, when two galaxies of comparable size collide, are transformative events. The collision unfolds over hundreds of millions of years as the galaxy's gravitational fields interact. Stars almost never collide directly. The distances between stars are so vast that even in a galactic collision, stellar collisions are extraordinarily rare. But the gravitational interactions between the passing galaxies create tidal forces that stretch and distort each galaxy's structure. Long tidal tails of stars and gas stream away from the collision site, some eventually falling back into the merged system, others dispersed into intergalactic space. The gas in colliding galaxies does collide, directly and violently. Giant molecular clouds slam together at speeds of hundreds of kilometers per second, creating shockwaves that compress the gas and trigger intense bursts of star formation. These starburst galaxies can form stars at rates hundreds of times higher than normal galaxies, converting much of their gas into stars within just tens of millions of years. The newly formed massive stars live brief lives and explode as supernovae, creating a cascade of feedback that heats the remaining gas and can drive much of it out of the galaxy entirely. The end result of a major merger is typically an elliptical galaxy. The orderly rotation of the spiral disks is destroyed by the chaotic gravitational interactions of the merger. Stars end up on random orbits, creating a roughly spherical or elliptical distribution rather than a flat disk. Elliptical galaxies contain mostly old stars, appearing yellowish or reddish because they lack the young blue stars that make spiral galaxies appear white or blue. They have little gas left for star formation, having either converted most of their gas into stars during the merger or expelled it through feedback from star formation and active galactic nuclei. Elliptical galaxies represent a kind of middle age or retirement for galaxies. They're massive, sometimes containing trillions of stars, but they're largely quiescent, forming few new stars. The stars within them are aging, slowly converting hydrogen to helium in their cores, gradually dimming as they exhaust their fuel. Over hundreds of billions of years, these stars will die one by one. Low-mass stars will swell into red giants, then shed their outer layers as planetary nebulae, leaving behind white dwarf remnants. Higher-mass stars will explode as supernova, leaving neutron stars, or black holes. As stars die, they return some of their material to the interstellar medium, but much of their mass remains locked in stellar remnants. The galaxy's gas supply dwindles, and with no new gas falling in from outside, star formation gradually ceases. The galaxy grows dimmer as its most luminous stars die and are not replaced. Eventually, in the far future, such a galaxy would consist primarily of white dwarfs, neutron stars, and black holes, the dead remnants of stars that once shone brightly. Some galaxies meet more dramatic ends. In dense galaxy clusters, high-speed collisions and gravitational interactions can tear galaxies apart. Ram pressure stripping occurs when a galaxy moves through the hot intracluster gas that fills the space between galaxies in a cluster. This hot gas, though tenuous, exerts pressure on the cold gas in the moving galaxy, stripping it away like wind pulling leaves from a tree. The galaxy is left with no gas for star formation, rapidly aging as its existing stars evolve and die without being replaced. Galaxies can also be tidally disrupted by close passes to much more massive galaxies. The tidal forces, the difference in gravitational pull between the near and far sides of the smaller galaxy, can be strong enough to overcome the galaxy's self-gravity, pulling it apart into streams of stars that wrap around the larger galaxy. The Milky Way is currently in the process of tidally disrupting the Sagittarius dwarf elliptical galaxy, a small galaxy that passed too close and is now being stretched into a stream of stars encircling our galaxy. In the very long term, over timescales of trillions of years, galaxies face a dark future. The expansion of the universe, driven by dark energy, is accelerating. Galaxy clusters will remain gravitationally bound, but individual clusters will become increasingly isolated from each other as the space between them grows. Within each cluster, galaxies will gradually merge, forming ever larger elliptical galaxies. Eventually, each cluster will merge into a single giant elliptical galaxy containing all the matter that was once in dozens or hundreds of separate galaxies. Even these ultimate galaxies will fade. Star formation will cease entirely as all available gas is either converted into stars or expelled from galaxies. The remaining stars will age and die. White dwarfs will cool, becoming black dwarfs, cold, dark stellar remnants that no longer emit visible light. Neutron stars will radiate away their heat over inconceivable timescales. Black holes will slowly evaporate through Hawking radiation, though this process takes vastly longer than the current age of the universe. 10 to the power of 10, 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 to the power of 10 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 to 100th power years for a solar mass black hole, far longer for the supermassive black holes at galaxy centers. The life cycle of galaxies is intimately connected to the larger evolution of the universe itself. In the early universe, galaxies formed rapidly and evolved quickly, building up their stellar populations and establishing their structures. In the current era, galaxies continue to form stars but more sedately, and many have settled into mature configurations. In the far future, galaxy formation will cease as the expanding universe spreads matter too thinly for new gravitational collapses to occur. The galaxies that exist will gradually fade as their stars die and are not replaced. But this distant future is trillions of years away. For now, and for the foreseeable future, galaxies remain vibrant systems. Star formation continues, though at lower rates than in the past. Galaxies merge and interact, transforming themselves in violent collisions that reshape their structures. New observations reveal galaxies at ever greater distances, showing us how they looked when the universe was young, allowing us to piece together the story of how galaxies live and die, how they transform over cosmic time, and how the universe itself evolves through the changes that galaxies undergo as they pass through their long but finite lifespans.